morning. It's 11:10. This is Physics 131. We're on to class 27 now. It's a nice sunny, warm morning in Toronto. So let's share my screen. What I'm gonna do is click share screen 2. That's the easiest thing. Oops. So hopefully you can see it there. This shouldn't do that. Get my participants list back and my chat. Okay, slides should be there. I only posted them about 10 minutes ago, so you might have to hit refresh. Still haven't gotten the hang of all this zooming. Somehow I've gone on to the next slide here, so we better launch a poll. So unfortunately, these are the same choices as last week, just because I sort of ran out of time. I was literally down to the wire, or figuratively down to the wire this morning. And since I've already got this big mustache going, I was thinking face filters may be a little redundant, but let's do it anyways. Why not, right? Give you 10 seconds to click in. Three, two, one. And polling. What does it say here? Happy Sprout. That sounds fine to me. So let me find it. Video filter. Nice little one there. I like the little cheek things. Okay, good. What else is going on here? Yeah, so this is this offset. So let me just delve right in to audio is an issue. I think I am using a different microphone. Arian, is that better? Okay, good. It is worse. There's two microphones that I can choose. I think in the past, people have liked it when I choose this. Let me test my own speaker and microphone. Yes, I hear a ringtone. Hello? Okay, so according to my Zoom, things are working sort of okay. So you may have to turn up your volume a little bit on your end. So I'm getting into chapter 9. She's got an observational experiment in which you have your bicycle wheel, which we actually, when I grab this, I brought an actual wheel. So if I push it in like this, then I get no turning. Okay, so that's kind of obvious. That's zero torque sort of situation. So as time goes on, it just sits there. If I push lightly and continuously in a counterclockwise direction, tangent to the tire, so which would that be? That would be counterclockwise like this. Then it gets faster and faster and faster and faster and faster. The more I push, the faster it goes. Okay. And then if we just release it, it'll just spin at a constant rate with its own inertia. That's observation experiment 3. And then with it going counterclockwise fast, you can gently push clockwise around the tire. The rotational speed decreases. So we can do that as well. If it's going like that and I push sort of upwards, it's a clockwise torque, and it slows it down. So this is the rotational form of Newton's second law. One or more objects exerts a force on a rigid body with rotational inertia I that can rotate about some axis. The sum of the torques, which is sometimes called the net torque, will cause the object to accelerate. and it'll be inversely proportional to whatever the rotational inertia is. So that's called Newton's second law for rotation sometimes. And then going back to this analogy chart, we have x was analogous to theta, v is analogous to omega, acceleration is analogous to this angular acceleration, force is analogous to torque, and mass is analogous to rotational inertia I. And that's, so when we look at Newton's second law, which we had before, it was the acceleration was directly proportional to the net force, the sum of the forces, and inversely proportional to the mass. Well, with something that's rotating, it's going to be directly proportional to how much torque there is, and inversely proportional to how much rotational inertia you have. So this is an example that people have been asking about on the Piazza. It's a Mastering Physics multiple choice question. And the issue here is that the book has a typo in the end of chapter solutions. I think the answer is E, at least unless I've got it wrong. But Mastering Physics is correct. It's the book which has got a wrong solution in the back. But why don't we just go through and do it? My notes. It's not that hard. It's a nice little example. So two discs are cut from the same uniform board. The radius of disc B is twice the radius of disc A. The discs can rotate around axes with negligible friction. Two very light battery-powered fans are attached to the disc as shown. When switched on, the fans that exert equal forces on the disc. So I'm going to say that FA is equal to FB. I'm just going to call that F. Okay. And what is the angular acceleration of the disc A in terms of that of disc B? You're asked to compare these. So what I think is that in both cases, we will use Newton's second law for rotation. Second law for rotation, which is alpha is equal to the sum of the torques divided by I. And in this case, the sum of the torques will be equal to the torque due to the fan, because it's on a It's on a horizontal surface. Gravity is certainly not going to accelerate it. The only thing that can cause it to turn will be the force from this fan. So for disc A, the rotational inertia, I, is equal to 1/2 times the mass of A times R squared. This is the solid disk equation. That's where that half comes from. If you look in your table of rotational inertias, if you have a solid filled in disk of radius A, radius R, and mass M, then the rotational inertia is 1/2 mr squared. What's m? Oh, yeah. So what we do know is that they're cut from the same uniform board. So what I think that means, I'm going to assume that the discs are made of the same material and the same thickness, right? Made of the same material of area density. I'm going to define a little area density, which we don't know, which will be sigma is equal to the mass divided by the area. Okay, so in this case, it'll be MA divided by pi r squared, because that's the area of a circle. Okay, so what that means is that MA is equal to, or MA, capital A, is equal to sigma pi r squared. So IA is equal to 1/2 times sigma pi r squared times r squared. So it's pi times sigma over 2 times r to the 4th. And then B, disk B, similar sort of thing, IB is equal to 1/2 of MB, but now it's got radius 2r, so it's 2r squared. So that's equal to the 4 squared, so 4 divided by 2 is 2, 2 times the mass times r squared. And similarly, it's the same material, so sigma is equal to the mass of B divided by pi times 2r squared, which is equal to the mass of B divided by 4 pi r squared. And so the mass of B is equal to 4 pi sigma times r squared. So IB is equal to 2 times 4 pi sigma r squared times r squared. So it's 8 pi sigma r to the 4th. So tau B is equal to, oh yeah, so that's another thing. The torques. The torque on A is equal to the force times R, but the torque on B is equal to the force times 2R, which is 2FR. So that's the other thing that we're going to need. So let's shift all this over. We see that sigma of A is equal to the torque on A divided by its rotational inertia. So it's FR divided by pi times sigma over 2 r to the 4th. So it's the 2 comes up, it's 2 times F over pi sigma r cubed now. And the angular acceleration of B, again, is torque of B divided by I B. It's 2FR, twice the torque, divided by, I think it's actually 16 times the rotational inertia for this disk. So I ended up with 1/4 of F over pi sigma r cubed. So alpha A is equal to 8 alpha B. Okay, and this makes sense, I think, since the tau of B is equal to 2 times the tau of A, but the rotational inertia of B is equal to 16 times the rotational inertia of A. Jerry, how are you doing out there?
Yeah, so just quickly asking for inertia B, isn't it 1/2 instead of 2 times the whole thing?
Well, there was a 4 in there, right?
Oh, I see. Now I see.
4 over
yeah,
2.
Was wondering. Thank you, sir.
That's where that came from. And Armand?
Hi, sir. I just wanted to know, what is that sigma equation that you have there with the mass over area?
Well, it said in the original thing that 2 disks are cut from the same uniform board. So what does uniform board mean? Well, it means that if you had twice as much area of board, you'd have twice as much mass, right? So that thing, I'm calling this sigma. Is what I call the area density, I guess. It's the mass divided by the area. That's going to be the same for any object, any shape that you cut out of that board.
Oh, I understand. Okay. And then why did you do 1/2 mass times radius squared again for the solid disk?
Because that's from the solid disk equation. So last time we went through all those equations for all the different kinds of shapes. There was sphere and hollow sphere and all that stuff. Solid disk was the 1/2 mr squared.
Oh, okay. Thank you.
Okay. Those are all great questions. And Jukin?
Hi, Professor.
Hi.
I have a question. Why the inertia of B is calculated by the mass of B multiplied by the square of R instead of 2R squared?
Well, it is, right? It's 2r squared. It's on this, but there's a half out front. And then I did the 2 squared was 4 divided by 2, and I got a 2.
Oh, okay, thank you.
Sure, you're welcome. Maybe one last one, Josephine?
Hi.
Hi.
So for the sketch and translate section,
Yeah.
how did you know to do that equation and not the last one that we learned, like on the pages before?
Well, this was it, right? This one, you mean? That's that.
Oh, got it. Okay.
Okay.
So why did we choose that equation?
Well, yeah, I guess that's part of the whole translate. I'm trying to figure out what they're asking. They're asking for angular acceleration. How do you find angular acceleration of anything? You're going to use this Newton's second law for rotation.
Okay. And then also on the same page, like the question.
Yeah.
How did you know to do this density thing? Like, where did that come from?
Yeah, well, I guess that sort of came from my head again. This is this uniform board thing, right? So they don't have the same mass. Probably the bigger board is going to have more mass than the smaller board, right? So my question to myself was, well, how can I figure out how their masses are related? Because when you look at this equation for rotational inertia, it's 1/2 mr squared. M is the mass of the thing, but a bigger thing will have a bigger mass if they're cut from the same board. So what's the same about them? Well, if it's the same thickness and it's the same like wood or something like that, then like the mass per area should be the same.
Okay, got it. Thank you.
Okay. Pretty tricky one, and it is interesting that there's this weird typo in the book, so that the book even got it wrong. It's E, not C. Okay, so moving right along here, I think we're going to get into this Teamup quiz, and it's all 3 questions on the Teamup quiz today are about the exact same system, which is this one. You've got a pulley. Okay, so what I haven't shown here is that this is a frictionless surface. Okay, so we've actually seen this kind of before. You have a mass M2 just sitting on a frictionless surface. It's connected by a rope, which goes over a pulley. And then there's a mass M1, which is hanging. And so what's going to happen is the whole thing's going to accelerate downwards, right? So, and then this thing is going to accelerate with the same acceleration towards the right. But now we don't have a massless pulley. We have a massive pulley. So what that means is that you're going to have a net torque on the pulley in order to give it some angular acceleration. And so what we're going to do here is if we define plus rotation to be counterclockwise, as we normally do, which is a little actually inconvenient in this particular example. But anyways, if we do that, then what we're going to have is the this acceleration, angular acceleration, is going to be negative of the linear acceleration divided by r. R is the radius of the pulley. So this is it's a bit of a tricky one. This is actually coming almost from the rolling without slipping. The idea is that the pulley is rotating without the string slipping over it. And so if the string is accelerating with acceleration A, then the pulley must be rotating with angular acceleration alpha, where the magnitude is A over R. Okay, and that's going to be radians per second squared. So how does it do that? There has to be a net torque. So I think what that means is that the tension in the ropes, so if you look at this on here, if you look at the force diagram of the pulley, you've got T2 acting to the left, and you've got T1 acting downwards, both with this radius r, okay? So one's gonna have a torque in one direction, one's gonna have a torque in the other direction, and it's gonna cause it to have angular acceleration in the way that it goes. It's rotating clockwise. So it's gonna have to be a negative torque, right? Negative net torque. Because negative angular acceleration. So A is positive in this thing. I just asked a good question. Okay, so that's the one thing. We're about to start the Teamup quiz, which is already posted on the Quarkus. You should be able to see it. Now there's another thing, another Crazy Friday thing. I know we're juggling a lot of stuff here, but there's 3 more Crazy Fridays. So what I thought I would do is a TV show bracket, today being the quarterfinals. So right after the Teamup quiz in 10 minutes from now, probably 11:43 maybe, at 11:43, we're gonna have this bracket. It's going to be really quick, 15-second questions, and I'm just going to ask you to choose one of these 2. So either Queen's Gambit or Better Call Saul, either What We Do in the Shadows versus Tiger King, either The Good Place or BoJack Horseman, or Schitt's Creek versus Parks and Recreation. So you choose your favorite for each of those pairs, and then the winners, the 4 winners, will advance to next week, and then we'll anyway get it down to 2, and then the last week we'll choose a winner. But that's all going to be done here in this Zoom room during using the polls. So we're on to Teamup. 3 multiple choice questions, all from chapter 9, all from that exact same situation. Pod team shares the mark. So right now, go over to Microsoft Teams. One of you should place the video call, get your pod members on the chat. You should all go to Quarkus, find Teamup Quiz Module 5, Chapter 9. Choose the driver over in your Teams window. Non-drivers then have to wait while the driver clicks on Create a Group. Then the driver comes back, gives the session ID to everybody. Then the driver should wait while everyone joins that session until you're all in the Teamup session. Once you're on the Teamup session together, then you can try to achieve consensus with the driver waiting, making sure everyone kind of feels good about the answer before you click and to go on. So again, right now it's about 11:32. I'm going to go on mute until 11:33. I may even pause the recording if I not to annoy the YouTube people again. I'm also going to go over to the Physics 131 Help Center and set up some breakout rooms in case your Teamup partners are not there. Sorry, YouTube folks, you missed the polls. The most exciting thing that happened was that Schitt's Creek got eliminated. Anyway, you'll see it next time. But I just went over question 1 discussion. It's B. Question 2. Where's my mouse? This is the harder one. So now what's going on is I need a negative torque. Okay, so acceleration is less than 0. So that means that the sum of all the torques must be less than 0. So if this is giving a positive torque, T2, and T1 is giving a negative torque, then I think that the T1 has to be the greater one. You could say. You have to have more tension pulling the thing clockwise than resisting the thing by pulling it counterclockwise. That's how this is all working. And then what is the net torque? Well, the net torque is going to be, if this is sort of R right here, it's going to be, the positive one's going to be T2 times R. And then the negative one is going to be clockwise one, T1 times R. And in both cases, what's happening, if you look at there's R and there's T2, there's a right angle. Theta is equal to 90 degrees, right? So sine theta equals 1. That's why there's no sine thetas in that. If the tension forces were equal, then you could not accelerate pulley. It's a massive pulley. If it's a massless pulley, an ideal massless pulley, then you don't need the tensions to be different. But anyways, T2 minus T1R, that's the torque. Okay. Why don't we just do the problem? Because we got a little time here. So when an object is attached to a pulley, the distance that the object travels is equal to the change in the angular position of the pulley times the radius of the pulley. Right? So the distance that M1 and M2 moves, if that moves, some distance S, and this moves some distance S down, then this pulley will turn some angle theta times R, where theta is the angle the pulley turns through. And then similarly, the speeds that they're going will be related to the angular speed of the pulley by omega times R. And similarly, again, we're just doing time derivatives, the accelerations of the two masses will be related to the angular acceleration of the pulley by alpha times R. So these are what I call the, they're actually very similar to the rolling without slipping constraints. I call them constraints because they're an extra equation which you can add to any other equations you might have. And what I want to do is this question. Give some numbers to this now and see what we get. So mass M2 equals 2.5 kilograms, right up here, is on a frictionless table. It is attached to a cord. So here's M2. It is attached to a cord that wraps around a massive pulley, just draw it like that, of radius R2. It's got R is equal to 0.2 meters, and I is given actually, which is nice. We don't have to calculate it. 0.05 kilograms, kilograms times meters squared. Oops. Okay. And then this thing's hanging down, M1 is equal to 0.75 kilograms. And it's asking you to find A, okay, the acceleration of the whole system. What's the acceleration of M1 as it falls, which will also be the acceleration of M2, and it'll be related to the angular acceleration of pulley. So we're going to assume no friction on either disc or on the pulley. So there's no friction in the axle of the pulley or anything like that. So let's start with the pulley system. So define the system as the pulley. What you've got, we can draw a force diagram. You've got the tension of 2 on the pulley, pulling it counterclockwise at some radius r, and you've got the tension of 1 on the pulley, pulling it clockwise. So the sum of the torques is equal to, as we saw before, T2 times R minus T1 times R. And alpha, Newton's second law for rotation, is that it's equal to the sum of the torques divided by I. So alpha is equal to R over I times T2 minus T1. And I'm going to call that equation 1 because that's the first system. If we look at the M1 system, this is just acceleration. We can just sketch it out here. Here's the force diagram. You've got T1 on 1 acting up from that string, string 1, and you've got the force of gravity of the Earth on 1 acting downwards. We're going to define plus y is down, so that the forces in the y direction is equal to m1g minus t1. The acceleration is equal to the sum of the forces in the y direction divided by m1. So the acceleration is equal to m1 times g minus t1 divided by m1. And we'll call that equation 2. Okay. So next step is to look at the M2 system. that's got a couple of irrelevant forces from the actual surface, right? So we've got the normal force of the surface on 2 acting up. And we've got the gravity force balancing that out of the Earth on 2 acting down. Those don't matter since it's not accelerating up or down. What matters is this, the tension of 2 on 2, pulling it towards the right. And we can define plus x to be towards the right here so that the sum of all the x forces is equal to T2, right? And the acceleration here is equal to T2 divided by M2. We can call that equation 3. And then the fourth equation, because we've got 4 unknowns, is that constraint. The fourth equation is the acceleration constraint. Okay. Note that when M1 falls, A is positive, okay? But alpha is clockwise. That's where the negative sign is going to come from, which is negative. So I'm going to say that A is equal to negative alpha times R and call that equation 4. So I've got 4 equations and 4 unknowns. 4 unknowns are T1, T2, alpha and A. And we want to solve for A and eliminate all the other variables. So equation 2 implies that M1 times A equals M1 times G minus T1. So that means that T1 is equal to M1 times G minus M1 times A. And equation 3, which we just worked out, says that T2 is equal to M2 times A. We're going to plug these into equation 1. And we get that alpha is equal to R over I times M2 times A minus M1 times G plus M1 times A. I'm going to plug this into equation 4, and I get that A is equal to negative R squared over I times M1 plus M2 times A minus M1G. Just going to rearrange that all. I've got A times I over R squared plus M1 plus M2 equals M1 times G. So A is equal to M1 times G divided by I over R squared plus M1 plus M2. So it's 0.75 is the hanging mass times 9.8. That's sort of what's driving it, so why it's on the numerator. And then what's holding it back is the rotational inertia of the pulley, 0.5 over 0.2 squared. Also the mass of M1, sorry. The mass of M1, which is 0.75, it's holding it back, plus also 2.5 kilograms of the top mass. So I got the acceleration is equal to 1.6 meters per second squared. And this is less than G, which you would always assume. If it wasn't if the string was cut, then M1 would fall with 9.8. But since it's a string there and you're accelerating all those things, it accelerates with less than that. Well, we're gonna have to wait for a couple of things here. Let me go through one more thing. I'm running a little low on time. There is a vector description of rotational motion. So you can do one-dimensional motion using V and force. But if you have motion in a plane like we've done, then you have to use vectors, V and F. Similarly, a more general description of rotation, we've been using omega and tau just be positive or negative. You can use vectors for omega and tau. And we can get angular momentum from this. To do this, we use what's called the right-hand rule. So the magnitude of the angular velocity omega is just omega. But the direction is given by the right-hand rule. So if you've got something rotating, what you do is you say that the angular velocity vector points along the axis of rotation, so perpendicular to the plane of the rotation. And to figure out if it's going up or down, you curl your fingers in the direction of the rotation using your right hand and point your thumb up, and your thumb points in the direction of omega. And then the angular momentum will be in the direction of omega. So that's an equation we'll get to next time. But I want to leave you with this one poll question. See if you can get it. So here we have tires. The car is going towards the right. What is the direction of the angular velocity, I guess, and the L? Also the direction of omega. So you're going to need to use your right hand here, figure this out. And you can also see these are going to be rotating clockwise, right? So I'm going to rush you a little bit on this one. And the polling results. So most people are saying E, that's into the page. And that's the way I look at it. I kind of got, if I'm going to curl the fingers on my right hand, okay, then the thumb will point into the page. So these are fingers. I don't know what that terrible drawing here. Thumb points into page. Away, right? Okay. So that's it. I've overplanned a little bit today. You guys have been very patient with me. So I do want you to finish up reading chapter 9 over the weekend. Something to think about. Why is there a tiny gyroscope in your telephone? So thanks very much. And I'm going to turn off the recording, go to raised hands.